In this example, we're going to compare the Timoshenko beam with the Bernoulli beam in ABAQUS. So we're going to analyze a cantilever beam with the dimensions of length is 5 meter, the width is 0.25 meters, height of 0.5 meters. Material properties are given here, Young's modulus and the shear modulus. The load is 10 meganewton. The effective area in shear is required for the Timoshenko beam. For a rectangular section, it's given in some texts as the shear area as 0.85 multiplied by the whole area, or in other texts it's given as the whole area divided by 1.2. The exact solution should be for Bernoulli beam 0.8 meters and for the Timoshenko beam 0.806 meters. So we're going to start by a part. This is two-dimensional, deformable wire. The length of the beam is 5 meters, so I'm going to start at 0, 0 and up to 5. Press escape, done. This is the part. I'm going to mesh it. Since this is I'm going to start with the Timoshenko beam and a linear analysis. All we need is actually one element, so approximate global size. I'm going to use the whole length. And for the elements, I'm going to click on beam, linear, cubic formulation. Cubic formulation is the Bernoulli beam, linear cubic formulation. Okay. And mesh. Okay, to mesh the part, yes. For the materials, it's elastic, 200,000. Now Poisson's ratio here is not going to be used, but I will also input it. Then we need to define the section of the beam. It's a beam. Continue. Since it's a linear analysis, we can integrate the beam before analysis and create a profile. The cross section is rectangular, so that the ABAQUS calculates the area and the eye according to the cross section. A is 0.25, B is 0.5. Okay, so this is the profile. The stiffness, the Young's modulus is 200. 1, 2, 3. And I need to specify the shear modulus, 77, 1, 2, 3. Although for the Bernoulli beam, this will not have any effect. Then I need to assign the section, this assign section 1. I also, for beams, need to define the orientation of the beam, and this will have the default orientation. Select the regions, done, and this default one will be appropriate. Okay. So after defining the material properties, the cross section and the beam orientation, then we need to define the assembly. Bring the beam, create a load step, apply the boundary conditions, this end is fixed. Apply load concentrated force at the far end. Add a value of -10. Create a job. I'm gonna call it 1. Alright, and submit. You can monitor for any errors. And the analysis is completed successfully. I'm gonna right click and bring the results. Plot the deformed shape. I'm gonna use the query tool, the node. Click on this node to see that I get the exact displacement using one element, which is 0.8 meters. The next step is to try the Timoshenko beam. So I'm going to go back to my model, go back to the mesh, and define a shear flexible. This is the Timoshenko beam. However, you have to be careful when you use a Timoshenko beam because it's the formulation is slightly different. Since it's the ABAQUS uses a certain linear approximation, and that's why for Timoshenko beam you have to use many elements per beam. So I'm going to show you the difference between using one element and a lot of elements. So I'm going to first use one element, okay, and mesh. Everything is the same. I'm going to let the software use the default properties for the shear stiffness. I'm going to show you how I'm doing this. Just when you look at the section, I'm not going to specify the transverse shear. I'm just specify the shear modulus and let the software calculate the shear stiffness. And submit. The results for the Timoshenko beam for using one element. Again, I'm going to use the query. And it's too stiff, 0.759, which is actually less than the Bernoulli beam, when in fact the Timoshenko beam should be less stiff, since it also allows for shear deformation. So the displacement here should be higher than the 0.8 meters that we obtained for the Bernoulli beam. So I'm going to go back and show you the effect that I'm of using more elements. So I'm going to use 0.1, delete the current mesh. Okay, mesh this part, and now submit again. And monitor the analysis. Again, use the query, the node displacement, and I get 0.806, which is exactly what I expect using a shear modulus of 0.85. Now if you want to know what the values of the section properties for the different areas. If you go to ABAQUS manual, and you look at the beam section behavior, or beam element cross section or orientation, not this one, choosing a beam element. Here there's a table for the shear factor used for different cross-sectional areas. So for a rectangular, the shear factor K is 0.85.